Good afternoon, everybody. As the title says, I'm going to be talking about ocean water level drivers and local data. I'm just going to start initially and just give you a very brief overview about New South Wales Public Works and Manly Hydraulics Laboratory. I just want to remind us all again as well what the objective of today is. And the way, in my simple term for it would be to improve everybody's understanding so that people are well informed in making decisions about sea level because it is a complex issue. And I hope if after my talk and after John's talk, if you can all learn something more about the science, that you will be better informed to make those decisions. I'm going to very quickly go through and talk about where and how we measure ocean water levels in New South Wales. Excuse me. And then I'm going to talk about why we measure ocean water levels, and it's not all about sea level rise. In fact, a lot of the monitoring has been started for very, very different purposes. And then I'm going to talk about what the driving forces are, the driving mechanisms for variations in the ocean's level. I want to spend a bit of time in that area because I think it's really important to give people an understanding of what we know about ocean water level drivers. And then I'm going to get into actually showing you some of the data in the area in the south coast of New South Wales, comparing and contrasting that data with other areas of Australia, and then also talking about some of the traps and pitfalls for misinterpreting the data, again to help folks to avoid that. Okay, so very quickly, New South Wales Public Works has been around for about 150 years, a long time. The reason I want to say something about Public Works, because Public Works today is very different to Public Works 150 or 100 or 50 or even 20 years ago. With changes to government, Public Works, a lot of you would know for building things like sewage treatment plants and sewerage and things like that. Other organisations, including local government, are responsible for those things now. Public Works today is really an area of expertise in a number of areas, particularly in the water engineering and coastal engineering environment, in data collection and things like that are important and underpin some of the questions that the community expect government to be able to answer in mitigating risk, particularly in terms of flooding, coastal erosion and those sorts of things. And I think that's a really important point. The rest of what I want to say about the background of who I work for is about Manly Hydraulics Laboratory. MHL was established in 1944. We've been around for a very long time. And in that time, we've been looking at coastal data in particular for a very long time, and we have continuous records dating back to the early 1980s, looking at how our coastal catchments and coastal areas behave. Manly Hydraulics Laboratory was established downstream of Manly Dam because it's got a large water supply, and it was established there to build physical models. Okay, the first physical model was of the dam spillway, and that was done in order to you don't want a dam to fail. The mathematics in those days was not as sophisticated as today, and we had to build physical models. Now, interestingly enough, we still use physical models for lots of our studies because of the complexities of interaction, particularly on the coast, looking at the complex interactions of breaking waves and structures on the coast. Physical models are still very useful. In the early 80s, a lot of the engineers and scientists that worked at the laboratory had a unique expertise in measurement, and that expertise, in order to keep the expertise busy, was used to monitor the natural environment. And from there, we started collecting data. Okay, now Phil's already mentioned, for the Office of Environment Heritage, we've been collecting offshore wave data. It's one of the richest wave coastal databases in the world that research is done overseas using that data. We also obviously collect other data. We collect drinking water quality for Sydney Catchment Authority and people like that. We collect the tidal information, which is really the focus of the talk that I'm going to give today. So where do we collect? there's over 1,000 locations that Manly Hydraulics collects data at, and several hundred of those continuously for many, many years, over 20 years. On the ocean, open ocean coast, we have over 20 locations where we have records dating back to the early and mid-1980s where we've been recording. You'll notice that Lord Howe Island and Norfolk Island also include sites that we monitor, and on the south coast there's a number of locations there where we monitor. We classify our monitoring stations according to those three categories, our ocean monitoring stations, and it's important that we understand this because it's one of the areas that we need to know the background when we're looking at the data. So we have offshore stations, and they're pressure transducers deployed out in the ocean, and they don't have any datum or any point of reference as such other than for that deployment. So we can get there 6 months or even getting closer to 12 months of data in one deployment, but when we're comparing years and years of data, we don't have a common reference. Okay? The other two locations, the onshore bay locations and the onshore river locations, they are actually on land, they're actually land tied, and they measure the ocean's level relative to the land. So we do have a datum, and that gives us some accuracy from year to year. But they also have other limitations. For example, the bays often have seiching effects. They kind of rock with long-term weather patterns, wind patterns or waves. And the river stations can also be affected by catchment rainfall runoff processes. Okay? But essentially, those locations have been selected to be representative of ocean levels. Okay, so how do we measure? Well, I've mentioned some already. I've been pressure transducers on the bottom, measure the change in pressure at the sensor. As the water level goes up and down, the pressure goes up and down. In the old days, we used to use a float in a stilling chamber to remove the noise from low frequency waves. We're interested in the tides going up and down, which are over several hours. And they'd originally be on a chart recorder. More recently, those are on a data logger, so we're getting digital data. We also use electromagnetic poles that can measure the movement up and down. And we can also, more recently, been using radar to measure the water surfaces. Now, you've got to realise that there's some averaging that needs to happen to those measurements. We're really interested in tides, which if you look at the level every 15 minutes or so, you're getting a pretty good indication of which way the water's going. If there's other things going on around there, wind chop, there might be other things like tsunamis and things like that occurring, you'll be wanting to measure things more frequently. Technology's been changing and the instruments have been improving, and the things that we can measure continue to improve. Satellites since the early 90s with low orbit satellites and continuing to improve have altimeters on them, and they can measure the sea surface level. Okay? Now, satellites measure the sea surface level relative to their position, and with calibration on the ground we can actually determine those sea surface levels relative to the centre of the Earth. Okay? So quite different to the tide gauges, which are relative to the local land. And we'll get into a little bit of that, and John will cover some of that as well in his talk. But it's important to understand the satellites give you a spatially averaged level, okay, over the width of the beam of measurement, whereas a tide recording station is one location. Okay? It's important that we remember that. Okay, so a little bit about, before I get into talking about tides and ocean forces, why do we measure it? Well, going back, a lot of MHLs in New South Wales coastal monitoring came about because of flooding, okay? And then it was underpinned by coastal erosion events of the 70s, 74 and so on. So a lot of the instruments were deployed for those reasons. But we've got to keep also in mind that with sea level rise and climate change driven, the world's climate is changing, and we'll talk a bit more about that. It's not only the sea levels that are changing. I mean, the weather patterns follow the warmer parts of the ocean, for instance, between the tropics, and with slight adjustments in those, Wave conditions, the frequency of storms, the intensity of storms, the magnitude and direction of waves on the coast can change subtly and undetectably during a particular event, but the frequency of a particular direction. For New South Wales, southerly waves are predominant. If that were to change by a few degrees more to the east, all of our beaches would want to rotate to realign to that dominant energy. The consequences of that can be quite significant. Wind and water levels also obviously affect both in terms of magnitude, frequency and direction. But our focus really is on ocean or sea levels and what effect they have on the coast. And really, I mean, straight sea level rise by itself is going to increase coastal flooding, okay? And it's going to also exacerbate erosion and or long-term recession, and quite simply because it just lets more wave energy. If the water's deeper, it just lets more energy onto the coast. The impacts on existing coastal structures can be quite significant, particularly given that the stability of a coastal structure is to a cubic power proportional to the amount of wave energy coming in. So if you get a 1 increase in wave energy, you'll get a 3 times increase, or a 2, you'll get a 2 to the power of 3 increase, which is like an 8 times increase in energy on the structure and instability of that structure. That's why small changes in level can lead to small changes in wave height, which can lead to large changes in instability. The height of the structures, obviously, as well, with larger waves, will be affected, what height they need to be to prevent waves overtopping and flooding. And the toes of the structures, with the greater energy, more scouring, predominantly coastal structures fail not from units being thrown off, although that can happen. They do fail from toes becoming unstable and the structures collapsing. So that's why. The real problem is when we put assets in harm's way. Okay, so none of these are issues, and as Phil alluded to earlier, we've been dealing with the dynamics of the coast for a long time. For a long time, we have not thought of the coast as a static area that you can design structures in. We've understood that they're dynamic. It's whether those positions of concern or those locations affected by the coastal processes are changing. I'd like to spend a little bit of time now talking about why the ocean goes up and down. Okay, so first of all, I mean, the world's oceans, I assume everybody in the room knows, have tides, right? And then the ocean levels go up and down every day. In fact, in most places in New South Wales, twice a day, and they're called semi-diurnal tides. The main driving force for those tides is gravity. Okay, the gravitational pull of the moon and the sun. Okay, the moon, in fact, has twice as much influence on ocean levels as does the sun, even though the sun is many, many, many times bigger than the moon. But the moon is closer to us, and that's why. Okay. The other force that's occurring is a centripetal force, the fact that the Earth is spinning both on its own axis and around the sun, which pushes, just like water in a bucket, when you swing it round, pushes the water, it keeps the water in the bucket. So you can imagine the centripetal force is acting in one direction, and the attraction of the moon and the sun is sometimes in the same direction, sometimes in the opposite direction. Okay? That picture tries to depict some of that science that's going on there. The relative position of the Earth, Moon and the Sun really affect the tide throughout the day, okay? And throughout the different times periods as I'll try to explain. So first of all, the Earth rotates, and everybody knows, 24 hours in a day, okay? And in that 24 hours we get two tides. Now the reason we get two tides, and if you look at that little animation there, the reason we get two tides is where the moon is closest to the Earth, we have a high tide, okay? On the opposite side, where the moon is closest to the Earth, we also have a high tide, okay? And because the Earth is spinning every 24 hours, you get a high tide twice a day, one when the moon's closest and one when the moon's opposite, okay? One's due to gravity, the other one's due to centrifugal force, Okay? What happens though, that in a 24-hour period, the moon is also going around the Earth, not just the Earth spinning. And it takes about 28 days for the moon to go around the Earth. That's the month, the old calendars were 28 days. And if you look at that then, over a period of 24 hours, the moon's actually gone around 50 minutes in a day. So that means that the high tide each day, and those of you that fish and get out and about and know about tides, will know that the high tide each day is 50 minutes later than the day before. Okay? And that's the reason why. As we move down to the next bit of understanding, the moon, as I said, goes round the Earth every 28 days. Every 14 days, the moon and sun are aligned, or every 14 days they're either aligned in closeness or far, so they form a straight line. And during those periods, those forces are greatest, and that's what we call spring tides. Okay? So every 14 days we get spring tides, and in the other 14 days when the moon and the sun are at right angles, we get neap tides, because the centrifugal and the gravitational forces cancel or they work together. Okay? So they're quite important things to understand, and they're reasonably simple to understand, but a lot of people might not have known that, and so I thought it was interesting to build information as we build complexity. Okay? So the next stage is every 365 days, the Earth goes around the sun. We all know that. And that's the year. And in summer on the southern hemisphere, the Earth is closest to the sun, which means that the sun's forces are slightly greater than when the Earth relative to the sun is further away. And as a result of that, we get slightly larger tides during the spring tides. The springs are the biggest springs of the year, and twice a year that occurs, and it's what we call in Australia king tides, and they occur in January and July. Okay? And again, it's due to that proximity. Okay? So it's not quite that simple though. So that's really like the geography lesson part of it. The realities is that the orbits aren't circular; they're actually elliptical. The orbits are also eccentric and inclined. That means that they're not perfectly relative to each other, and over time, over years, for instance, the inclination of the moon and the sun's orbit, Earth's orbit around the sun, come to the same place only once every 18.6 years. Okay? And that's what's called a tidal epoch, and we use that period to determine all the constituents for the tide at a particular location. Okay? It gets more complicated than that. I mean, the Earth itself, the sun itself isn't still. If you imagine the whole of the galaxies and everything's moving relative to each other, and that introduces all sorts of other timescales. Okay? There's the Milankovitch cycles, as the literature refers to them, which the eccentricities of the inclination of the Earth changes. It's like a spinning top that's kind of rotating. And that inclination change, by only a few degrees, 5 degrees, as well as other eccentricities out there in our solar system, are believed to be the causes of things like ice ages every 40-odd thousand years, or 100,000 years. Okay? It gets more and more complex as you try to explain more and more of this stuff. Okay? And this is science. So that's the easy part. If we push the moon away, okay, which is our main forces, there's other things, non-astronomical. We refer to those as astronomical factors, okay, that affect our ocean levels. There's other things that affect our ocean levels, and quite tangibly so, okay. So the first two there, barometric effect, which is when low pressure systems or high pressure systems are existing over our space, we get a rise or fall in water level, and that's directly proportional. You get 1 centimetre rise in water level for every hectopascal drop in pressure. Okay? Wind. When wind blows on a water surface, particularly over shallow water, the water level will rise downwind and drop upwind. Okay? Steric effects refer to the density of the water by both its salinity and temperature. Okay, so denser water will be more compact. Warmer water, less salty water, will be less dense and relatively higher. I mentioned there the East Australia current, which also transports water into or out of an area. So if you pour the hose into an area, the water level will go up. Okay, just the same way, the East Australia current is transporting water in and out of different areas. We also have mentioned seiches before. These are standing waves. It's like when you push the bathtub around. That's a standing wave, and you can get that happening in the big ocean, and you can get that happening in bays and other areas. And they're driven by meteorological events, like in New South Wales. Those are driven by weather down in Bass Strait. Okay? They can cause coastally trap waves, where waves actually underwater can break in a surface that's created by a temperature difference or a salinity difference, and waves can then be breaking on that surface and get trapped against the coast and elevate or decline our coast, our water levels. Wave setup: when waves break, they push water to the shore just like currents, and that can set up the water level on the coast up to 1.5 metres during major storms. And of course, tsunamis, even in remote places, can affect our water levels. I'm just going to flick you very quickly now to some examples. That graph there, the zero, which is kind of there, okay, and then you've got 0.2 plus and minus 0.2 metres, okay, up to 0.4, 0.6. Are the difference between the astronomical and non-astronomical tide. So that's the difference between the predicted tide, which we can predict quite accurately. The science of that is well understood, and what we're actually measuring. And the reasons for those are things like high pressure cells off the coast, east coast lows, or as that little picture shows you, when the East Australia current extends further south than normal, it will elevate the levels at a location where they're not normally as elevated. And we call those tidal anomalies. The March 2011 tsunami in Japan, you can see there in Eden the tsunami being measured at your tide gauge. Okay? So you can see the blue line there is the tide going up and down, and the red line is the difference between the predicted tide and the anomaly. Okay. So, just summarising then, we can try and group the ocean's response to the different forces under different timescales. So in the short term, daily the tides are going up and down twice, and weather systems are impacting through the course of the day. Right? Even the changes in solar radiation from the morning to the night and the day will affect the levels. The monthly spring tide and neap tide cycles and the weather patterns that persist, and then on an annual basis, the king tides and the seasons, the persistence of certain weather systems for certain periods of the year, westerly winds versus southerly winds and those sorts of things. So that's quite easy to understand. Then there are longer cycles over 3 to 5 years. You would have heard of the El Niño and La Niña, or the ENSO cycles. These cycles set about oscillating in 3 to 5 year type periods. They're less known. We've known about them for a long time, but they're less well understood, and they're to do with relative positions of warm and cold water in the bigger ocean. Interdecadally, so cycling over 20 to 30 years and returning every 50 or 60 years, we have other patterns being set up in our oceans in response to some of these other longer-term cyclic behaviours that are going on. Again, less well predictable, but we have measures of those things. And then longer term, of course, all of those other things that are going on out there, which is in the timescale of what we're interested in with sea level rise, okay, which are occurring over, with all of these time processes occurring. Now, I've still got a few slides, so I'm going to have to try and flick through these fairly quickly. I just want to make the point that, sea levels, we're talking about 0.9 or a metre change in sea levels. Sea levels have been through 120 metres, and this is undisputed. So the sceptics of sea level rise and all of that would agree with these facts. Sea levels have been through massive change, and John's going to spend a lot more time talking about this. The area we're in at the moment is an area of relatively very stable sea levels over the last 6,000 years. The other thing to note is that the tidal records that we have are of limited duration, albeit the longest ones are getting close to 100 or over 100 years, which is fantastic. But a lot of the timescales that we're talking about with those interdecadal cycles and other things are operating over those kind of timescales. Okay? Sea levels, that's an average sea level plot for Fort Denison. Sea levels aren't static. There's no mean sea level isn't a mean sea level. It's changing every year because of all of these things. Okay? Whether there's a long-term change, that's the issue. Okay? And what's driving it. If you put trend lines, straight lines, which is 1 millimetre per year, 3 millimetres per year, 10 millimetres per year, if you put a straight line through it, it's not a straight line. Okay? You want to be pretty certain about what's going on if you're going to put a straight line through it. Okay, I said I was going to show you some data for the area. So from the top down, we've got Sydney, Jervis Bay, Bermagui and Eden. Okay, and what you see, you won't see too much detail there, but we can put straight lines through that stuff to look at sea level trends, not sea level rise. These are mean sea level trends. And we can see there that consistently, it's between one, if you look at the full data record, it's about 1 millimetre per year on average. But if you look at the more recent time since 1993, there's about 3 to 4 millimetres of rise there. Now, is that because of accelerated sea level rise or climate change? Or is that an interdecadal cycle? We don't know the exact answer from the data because the data's looking back, okay? But certainly, and John will cover some of this, the modelling and the intergovernmental panel, which is charged with this internationally to look at this stuff, believes there's overwhelming evidence to suggest that that it is actually there are accelerations taking place. Okay, in recent times. Just the graphs down the bottom, you can see also Port Kembla. I can put all sorts of lines through Port Kembla. 10 millimetres a year down to 0 or even negative if you draw it for periods where it's dropped down. So just be very careful about drawing straight lines through what is an undulating water surface. The other two plots show you there's a couple of months of data, so you can see the spring neap. There, spring neap cycles, and there's a couple of years of data there, so you can see that we're putting straight lines through that sort of data when we're trying to put straight lines. Okay, even getting an average for 1 year. If we join up some of the local data and put it with some of the longer records, like for Fort Denison, we can see that the behaviour is very similar. That's mean sea level for different tide stations, including Fort Denison and some of your local gauges, and they're exhibiting similar behaviour. Now, they may be temporarily out of phase. In other words, it starts raining in Sydney, it's not going to get to Wollongong for a while if it's travelling from the north and so on. These ocean systems are the same. They're not necessarily fully in sync, but averaged over time, we see similar processes occurring. We can relate these to indices, and I won't go into this, but there are indices that we can relate and see why the alert levels go up and down. That's the interdecadal Pacific Oscillation, which the Bureau and others talk about on their website, and we can see that mean sea levels, if you take the average 0.9 millimetres per year out of Fort Denison and then detrend it against the IPO, you can actually see that it follows those patterns. Okay. So I should say something about the traps. Really, sea levels go up and down due to a number of factors, okay? Some of those we understand quite well, some of them we're continuing to understand better. The changes that we get, and that both in temporal over decades, some of those changes, and some of them over days, range from plus or minus 0.2 to 0.6 metres. They're quite significant numbers. Okay, when we're talking about changes in sea levels of 0.9 millimetres per year and so on, it's in that context. Okay? So it makes it difficult to determine straight line trends just out of the data. Okay? The other thing that is important to note is that sea level rise and sea levels generally are not the same around the world, and the picture there just shows you the relative sea level rise that's occurred from satellite data over the last 20 years. Okay? And the reason for that is because different parts of the Earth are exposed to different amounts of solar radiation or warming, and they'll respond accordingly and they will react accordingly. Okay? So it's not uniform. The other thing to note is that, just to remember that we can measure sea levels geocentrically, as the IPCC do, an average over the whole globe, or specifically at particular locations, or relative to land. And the land can be moving too. Okay? And that the global average sea level change that is looked at with all the best information may not be the average for a particular location. Okay? So I think I've covered most of this. Linear trends, not necessarily representative of what's going on locally or in the long term, particularly where the data is barely covering the length of some of these cycles that occur. Okay? The record length, start date and averaging method all have a massive effect on the trend. I can give you any trend you like, okay, just by choosing when to start and end. But, you know, that's not what the science is about. The science is about trying to go through all of that detail, unpin the things we know and we don't know, and assess what the long-term trend may be. Okay? And that's where all the effort is. The implied accelerations could be due to some of these cycles, but there is strong evidence to suggest that there are other anthropogenic or man-induced influences, or whether they're local or natural. You know, the climate's been changing forever. Climate's not static. We average it over 30 years, but it's not static. Okay? Fort Denison does provide a good surrogate in terms of dynamic change for what's happening in the rest of New South Wales. So while I said that sea levels aren't rising the same everywhere globally, certainly in New South Wales, the trends and changes between Sydney, Port Kembla and Eurobodalla region are not significantly different. Okay? Similar processes are occurring. And ongoing monitoring really is essential in order to be able to understand what's going on as we move forward, both in terms of what's going to happen, what's happened, and making decisions about when certain triggers or certain thresholds may be exceeded. Okay. So, summing up, despite all the complexities and uncertainties that exist, there is undisputed evidence that the world's climate is changing. No one's actually questioning that, whether it's anthropogenic or natural. Sea levels are rising. There's no dispute around that. Whether or not it's accelerating and whether or not it's caused by man, it still requires us as professionals, as an engineer, if I'm designing a coastal structure or assessing a coastal development, I have to consider sea level rise. Okay? Otherwise, I would be professionally negligent because all the evidence points that it's occurring. The other thing which some of the speakers earlier spoke about is that taking steps to mitigate the impacts of sea level rise now as opposed to waiting for those impacts to occur, because even though sea levels rising very gradually, the impacts won't be felt until there's the next major storm event. Okay? And if we wait for that storm event, then the damage to repair that is a lot less, in fact, orders of magnitude less according to the Stern review, and I think these reviews are being updated. We actually will save a lot of money. Okay? I hope I've been able to demonstrate to you that there's a lot of understanding around this stuff. Obviously, in a short talk, you can't cover everything, but you do need to rely on the appropriately experienced practitioners in providing advice. And there's international. We're very fortunate to have John speak to us this afternoon. and to rely on their information and to rely on people that are experienced on the coast to help interpret some of that information. Okay? And perhaps the last picture there we can talk about later, which is really about how we should deal with all this stuff. And it's really through some kind of toolbox that allows us to consider the risks and make decisions. Okay? Otherwise, we'll end up with a coast that looks like that. There's a lot of examples in the US there. There's the sheltering palms in Brunswick, New South Wales. If you do individual coastal protection, as that example shows, inappropriate design of coastal protection, rocks were thrown through those houses. That's what the holes in the walls are, where rocks were actually thrown through. And you also still end up with erosion around those areas. So these are things we've been dealing with for a long time on the coast. The sea level rise is happening gradually, so they're things we can deal with over time. Thank you.